guess, right? Let's do that. Wow, that was a lot. Let's. Wow, this is amazing, by the way. My God. Wow. This is why they don't, you know, skip step-by-step approach, because it's like impossible. Wow, if I can write this, if I can, yeah, type this in a Word file and translate it to a PDF file or something, and maybe share it with you guys, that will be awesome. I hope I can get that done. Wow, that's great. I'm happy with that result. So, you know what, maybe we should just I'm going to try to fit the necessity part to the right side of this. Okay, I just need to copy that, I guess. Right. Okay. And before that we prove this part was like the sufficiency, and now we are going to prove the necessity. And yes, well, let's remember the definition of H infinite norm, right? Like supremum of omega in real sigma max okay, and let's, yes, before that, like 1 minute ago we were using this, and I want to request something. Just please forget that notation, because we are going to use this symbol, phi symbol, in really another, to indicate another term. So just forget that, okay? Alright, let's use phi of s equals gamma square identity minus. Yeah, Zoo always uses that notation, and I'm going to explain that a little. This is like Hermitian, okay? Just alright. Alright. Then gamma if and only if greater than 0 for omega in reals, right? And this is like, this comes directly from the definition of here, H infinite norm. And also, since phi of infinity equals r, and it is positive, definite, and I want to expand this, elaborate on this a little. So we all know g of infinity equals d, right? Right, for example, g of s equals c, s I minus a inverse b plus d, right? So if s goes to infinity, this goes to 0, and we only have d term. So we can write this, and g of infinity equals d, right? And using that, not using that definition or information and this definition, we are going to have phi of infinity equals gamma square identity minus d transpose d, right? D transpose d. Here g tilde infinity and g infinity, right? And they're all right, d and d transpose equals r. Alright, and since phi of j omega is the continuous function of omega phi of j omega greater than 0 for omega in r, if and only if phi of j omega is non-singular for omega in real and plus or minus infinity. This is like extended real line. And let's focus on this if and only if condition. I mean, if that is like positive, yeah, it is obvious that is going to be non-singular, but this being non-singular, not that obvious. I mean, this being non-singular implies this being positive is not obvious. So non-singular. Okay, well, let's remember one thing. What was it? Yes, here is the key statement. Phi of j omega is a continuous function of omega. Okay, this is a continuous function. All right, so and we stated that is the case, and think of it like minus infinity and plus infinity. Here this is omega, right? And here this is like the spectrum of phi of j omega, right? And let's say there are 3 eigenvalues or something, okay? And since phi of infinity equals r, and this is like 0, meaning eigenvalues of phi of is or greater than 0. Let's say there are phi 1, phi 2, and phi 3, right? Alright, and this is also the case for minus infinity, okay? And this being non-singular implies this is positive, okay? And for example, what I'm saying is that this being non-singular cannot imply that phi of j omega is less than 0. Like 3 eigenvalues is like this, okay? This is negative, right? Cannot be like this. Why it can't be like this? Because let's say there is some omega 1, and here 3 eigenvalues. Let's consider there are 3 eigenvalues is like negative. That means, and since this is continuous, there will be some zero closing, and this zero closing is not allowed because it is non-singular. It's a contradiction, right? Well, I'm going to delete this embarrassing explanation, so, and you may want to forget that. Okay, this is my hand wavy, really hardcore hand wavy definition. And after that, phi of j omega is non-singular for omega in real if and only if phi of inverse s has no imaginary eigenvalues. It is not correct statement. Imaginary axis, pause. Okay, well, I'm looking at this here, and okay, G of S is A, B, C, D, right? This is the state space representation, and this is the transfer function representation, right? Okay, and we also have phi of S, right? Phi of S, what was it? It was gamma square identity minus g theta of S and g theta, right? Okay, what I'm trying to say is this is a transfer function, and since this is a transfer function, there should be a like A, B, its own A, B, C, and D, right? Okay, so if, and since phi of s is a transfer function, phi of inverse of s is also a transfer function, right? And this is also is going to have its own a, b, c, and d, right? State space representation, because it's a transfer function, right? And since phi of s has no imaginary axis poles, that means I want to say A, B, C, D. That means the A matrix, or rather the eigenvalues of A, right? They are all going to be real. There, or rather, real part of them is not going to be zero, is what I'm trying to say. They are not going to be located here, 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 right? Okay. So, and I'm kind of going to skip some steps. Okay, just rather j omega equals I'm going to assume gamma as 1, right? Identity minus g of j omega conjugate, right, times g of j omega, which is like equals I minus E transpose j omega identity minus A minus conjugate C transpose C, and j omega identity minus A inverse B, identity minus B transpose minus j omega identity minus A transpose inverse C transpose C, j omega identity minus A inverse times B equals identity plus B transpose j omega identity plus A transpose. I hope I'm not making a mistake. No, it's okay, inverse C transpose C, right, times j omega identity minus A inverse B. Okay, well, if we really try hard, we can notice that phi of s is A 0 minus C times C minus A transpose. No. I'm going to just write, come on, I'm just going to write this, and also D transpose C, B transpose, this is B, C minus B, C transpose D, right, and R Okay, okay. This is like a hat, b hat, c hat, d hat, right? Of this phi of s transfer function. So by using where is it? There was some inequality. I was using a little while ago. Okay, perfect. All right, just read a remark. Okay, if g of s is a, b, c, d, right, then g inverse is a system, is its, and g times g inverse is an identity, right? What I'm trying to say is this: g and g inverse system will be like an identity, right? Okay, and this system's state matrix is A minus B D inverse C, okay, minus B D inverse minus B D inverse C. Okay, all right, let's try to keep that in mind, because we want to find the phi inverse of S A B C, its own A B C D matrices, right? And to do that we're just going to use this identity. Okay, let's do that one step at a time. Okay, let me use another color. What does it say? A minus, and here the A minus B, here B minus B, C transpose D, A minus B, D inverse, here D inverse, C, here C, D transpose C, B transpose, okay, yes, right, here minus B, okay, it says B, right, minus B, C transpose D, okay, and D inverse, it says D inverse, and here D, right, R inverse, and again R inverse, here D, okay, and D inverse times C, R inverse D inverse times C, here the C, no, D transpose C, and B transpose, right? Okay, so this is phi inverse of S transfer functions state space representation. Alright, this is perfect. So the only thing that we know at this point is that this object doesn't have pose on imaginary axis, meaning its state matrix, and here when I say state matrix, it's like this again. Remember this is like A B C D, right? Like A hat, B hat, C hat, D hat, right? This is like this. its A matrix doesn't have eigenvalues located on the imaginary axis, right? So its state matrix doesn't have lambdas on JR. Okay, so and I'm going to call H, I'm going to call this matrix H because of the historical reasons. A 0 C transpose C minus A transpose, okay, minus B C transpose D R inverse D transpose C B transpose. Okay, yes, I'm doing this to differentiate between the lines, right? And let me state let me expand this here. H equals A plus B R inverse D transpose C minus C transpose identity plus D R inverse D transpose close the bracket C, okay, B R inverse B transpose minus A plus B R inverse D transpose C transpose, the whole bracket terms. Well, okay, I'm going to stop for a while. Alright, continuing. Now I'm trying to explain this Hamiltonian stuff. So, okay, just for a second, let's remind ourselves what steps did we take, right? First, we had this x dot equals ax plus bu, y equals cx plus du. Okay, g of s, and that was our state space representation. This is notation, okay. Alright, we had this, and then we computed phi of s, okay, which was gamma square identity minus g tilde of s g of s. By the way, you know what, I'm going to be more repetitive this time. G tilde of s equals g of minus s Hermitian, right? And again, Hermitian is, for example, a1, a2, a3, a4, and ai in complex, okay. And Hermitian of this matrix is like transpose conjugate, okay. So a1, a2, a3, a4, and we take the conjugate, right? Okay. For example, in single value decomposition, value decomposition, we use this operator, Hermitian operator, right? For example, A is second. Right, I messed it up. U, capital U, sigma, and V, and in most of the sources you see this asterisk, right? Or you see this Hermitian. Okay, this is like SVD, single word decomposition. By the way, single word decomposition is very important in Kontlev. So let's, for a side note, what was G infinity? It was supremum, right? Supremum omega in R, right? And sigma max, this is like sigma max. I could have written sigma max as well, right? And sigma max of G of K, continuing J omega. Alright, so to give you an example, for example, let's say G of S is like 1 over S plus 1, okay, 1 over S plus 1, S plus 2, 1 over S plus 3, and 1 over S plus 5, okay. Let's say it is 2 inputs and 2 outputs MIMO transfer function. So we are going to substitute J omega for S, right? And we are going to get G of J omega. Let's do that. To do that, I like to do this, and also I like to copy, paste. Wow, this is great. I'm getting better at this. Okay, anyway, J omega plus 1 and J omega plus 1, J omega plus 2, right? This is really this is really small. J omega plus 2, J omega plus 3, J omega plus 5, right? Okay, I just substituted J omega. Alright, and then what we are going to do is this. We are going to construct a grid, okay? So this is omega radian per second, right? I mean, since this is going to be a logarithmic plot, there's no, right? Okay, 1 second. So this is like infinity, and this is like really small number, and we are going to use omega 1, omega 2, dot 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 dot, and omega n, right? And for all of them we are going to, I'm going to say G1, okay? What is G1? I just substituted omega 1 for omega 2, okay? So we can generalize this. Omega I, right? Okay. And again, this is a matrix, and omega 1, for example, is a number, for example 0.1, okay? So, and G1 is 0.1 j plus 1, okay, and 0.1 omega plus 1, and again a mistake, 0.1 j plus, because we substituted for omega, okay, and what was it, 1 and 0.1 j plus 2, okay, and 2 over this term, and 1 over 0.1 j plus 3, okay, 1 over 0.1 j plus 5. Okay, this is a complex 2 by 2 matrix, okay, and single value decomposition, right? We can take a single value decomposition of this matrix, right? All right, and since this is 2 by 2, we are going to have sigma 1 and sigma 2 for G1. Okay, that's perfect enough. Let me just arrange this. Okay, and here this is our grid, omega 1, omega 2, dot dot dot, omega n, right? And then we have, for each omega term, we have G1, G2, dot dot dot, the respective G matrix, right? Gn, right? Okay, and since this is 2 by 2, we are going to have since this is 2 by 2, we are going to have sigma 1 and sigma 2, but we only need sigma max, okay? So we could have just drawn, for example, let's say this is sigma 1 omega plot, right? And this is going to be like this, sigma 2 omega, right? So we only need sigma max, is what I'm saying, okay? But you can, again, you can gather sigma 1 and actually sigma 1 1, sigma 2 2, okay? You can gather sigma 1 2, sigma 2 2, dot dot dot. You can gather those sigma terms as well, but I'm only going to focus on sigma max terms. So I'm going to say sigma hat, no, sigma bar. I could have written sigma max for the ease of notation, right? Sigma 1 and sigma bar 2, dot dot dot, sigma bar n, okay? Right, that's perfect. Now, since we have omega terms and we have sigma terms, right? We are going to plot this omega, okay? And this is sigma bar depending on omega, okay? And we are going to just plot this, okay? And let me get another color, okay? Here, right? This point is omega star, let's say omega star, or omega m, rather, I might say omega m, and this point is sigma bar m, okay? And this sigma bar m is h infinite norm of this transfer function. Okay, that was a comprehensive example, but let's delete all this. Let's delete all this, okay, because that was just a quick recap of the general concepts. Let's zoom it out a bit of. Right. Okay. Delete. It's funny, I just get distracted because I talk all of this because I was trying to highlight the meaning of Hermitian. Okay, that's fine. And yes, these are all unnecessary for this. Again, this is notation. Alright. H of minus s, Hermitian, h of s, okay, and again this is a transfer function. Phi of s is a transfer function, okay, transfer function, and so it has its own state space representation, and like for example 1 of s plus 1 is a transfer function, right? Let's say s plus 3, this is a transfer function. Let's say this is phi of s, and phi inverse of s is s plus 1, s plus 3, right? Okay, since we get this, okay, done. Sigma, no, phi inverse of s is, since this is a transfer function, we are going to find its own a, b, c, d, right? I just make this notation, I just use this notation, and we are going to call state matrix of phi inverse h for, just use this, h is Hamiltonian, okay, alright, and a couple of things to say about Hamiltonian is, first, it is a I don't want to use fancy terms. Real imaginary, this is complex plane, right? Hamiltonian's spectrum is symmetric about the imaginary axis, right? For example, if lambda is an eigenvalue of h, so does minus lambda conjugate, okay? What I'm trying to say is this: 1 plus 3j, if this is eigenvalue, minus 1 minus 3j, okay, and minus 1 plus 3j, okay, 1 3, alright, let's say this is lambda, alright, and 1 3 minus 1 dot dot dot, this term This is lambda and this is minus lambda bar. Okay. Again, these two terms are symmetric about JR to indicate imaginary axis. Alright. This was a long detour. Okay. Its spectrum is symmetric but JR. This is one, right? And two, it doesn't have an eigenvalue on JR. Okay. By the way, if I kinda okay, GH infinity less than gamma. Okay, if that is correct, if that is correct, if that's correct, if that's correct, then H doesn't have imaginary eigenvalues. Okay. Alright. How do we know this? I mean, we just proved it like a minute ago. Alright. Again, let's remind ourselves. Phi inverse doesn't have poles on imaginary axis means it's state matrix, which we call H, right? Doesn't have eigenvalues on JR, imaginary axis. Okay, that's great. And okay, since we mentioned that Hamiltonian matrix is a not only due to the historical reasons or conventions rather, Hamiltonian matrix is a special matrix in control theory. Okay, and for example, in algebraic Riccati equations or continuous time algebraic Riccati equations, for any algebraic Riccati equation, there is a Hamiltonian H matrix. Okay, and now I'm going to talk about this. Okay, let's say, for example, algebraic Riccati equation, right? Let's say A transpose X plus X A. Again, we could have written X rather this, we could have written this, right? Plus X R X plus Q equals 0. And Q and R is symmetric, right? Okay, we know for a given A, R, and Q, right? And notice it's almost like ax squared plus bx plus c. It's almost like that, right? but here x, the unknown or the dependent term, is a matrix, and this is called algebraic Riccati equation. Okay, and we want to find x. Okay, and we are going to construct H. There exists a Hamiltonian H matrix, or H, known as Hamiltonian matrix, associated with this algebraic Riccati equation, and it is written as A R K minus Q minus A transpose. Okay. Alright. Why this Hamiltonian has something to do with this algebraic Riccati equation? It is because we want to find x, right? Okay, and x is found by using stable eigen, or rather using x is computed by using the eigen vectors associated eigenvectors of H associated with the stable eigenvalues of H. Okay, or I could written corresponding to. Alright, so again, I am considering to make a standalone algebraic Riccati equation YouTube video, so I'm not going to say much more about this. Okay, we only know this, we only keep that in mind, keep this blue part in mind. Okay, so and Hamiltonian is a, since this spectrum is symmetric about the imaginary axis, there exists an algebraic Riccati equation with this Hamiltonian matrix as well. Okay, so for any algebraic Riccati equation, there exists a Hamiltonian, right, associated with this algebraic Riccati equation, and also this is the relation is reciprocal, right, for Hamiltonian matrix. And when I say Hamiltonian, I'm trying to say a matrix whose one which doesn't have an eigenvalue on imaginary axis, and two, its spectrum is symmetric about imaginary axis. Okay, for any Hamiltonian matrix there exists an associated algebraic Riccati equation. Okay, wow, that was a long explanation, but that was actually a good thing to keep that in mind. Okay, Hamiltonian matrix. Okay, so okay, what was our Hamiltonian? Let's copy this. Copy. know. I make this mistake all the time. It's very annoying, but okay. Copy and scroll down with your finger and then, oh come on man, just, wow, that's perfect. I didn't know that. I really didn't know that. Okay, all right. Okay, and let's use, yeah, bu use okay, bu use okay. And since this is Hamiltonian matrix, and since this is the algebraic equation associated with that Hamiltonian matrix, right? I'm just going to S A R or A bar, R bar minus what? Minus Q bar minus A transpose bar, right? Okay. So A transpose X. What is A? A here, this term. Okay. A transpose A plus B R inverse D transpose C. Okay, this was the A hat, right? Transpose X, there is X plus X. A plus B R inverse D transpose C. Okay, plus okay X, and what is R? R is this term, okay, here, right? B R inverse B transpose, okay, and plus Q, this is minus Q, and we are going to use plus Q bar, actually, C transpose identity plus D R inverse D transpose C. Okay, and this is equals 0, but I don't have any space. Let's try this. Hope it works. Okay, all right, step by step. Okay, this is the algebraic Riccati equation associated with this Hamiltonian. All right, this is algebraic Riccati equation. Okay, and now okay, I'm going to recap the every step again, once again. Okay, we have g of s. It is represented as a, b, c, d by its own state space matrices. Okay, and its h infinity norm is less than gamma. Okay, and then we then found phi of s equals gamma squared identity minus h of minus s Hermitian h of s. Let me check my notes. Where is this? Yeah, that's correct. Okay, and then we determine phi inverse of s. Okay, and we just obtain its Hamiltonian matrix. Okay, Hamiltonian matrix is the state or the A matrix of this phi inverse. Okay, and from this H, or rather from this H, we then computed the algebraic Riccati equation, or we constructed the algebraic Riccati equation. Okay, and yeah, that was it. Okay. Okay. So at this point we have this linear matrix equality, LMI, linear matrix equality. Okay. Enough. By the way, this is a really important equality right now. Enough. And let's use G hat whose state space representation is A, okay, and B epsilon identity, okay, where epsilon is like really small number but positive one, okay, epsilon 1 but positive, okay, and C epsilon identity, okay, D 0 0 0 0, okay, this is D, right, okay, and we can show this C, you know, G is like C B plus D, right? This is like something we know by heart at this point. Okay, inverse. Okay, M plus D 0 0 0. Alright. Well, I mean, you kind of have to persuade yourselves into thinking that what I'm going to explain you in a really hand-wavy manner is something that is intuitive. So epsilon can be chosen such that G hat of H infinite norm of G hat is less than gamma when H infinite norm of G is less than gamma. Okay, alright, and let's remember this equation once again, and if we use this equation, let me actually, I guess I already saved that, right? No, I didn't. Okay, let me use this, right? Oh my god, this is very hard. Copy. Okay, scroll down, press this, copy. Oh, that's perfect. Okay, this algebraic equation is associated with G, okay, and we are going to construct the same, not same, we are going to construct the algebraic equation associated with G hat, okay, and so we are going to use, for example, let's focus on this term, right? Focus on this term, and A plus B. What's B for G bar? B epsilon identity. Okay, R inverse, or rather let's look at the R. R is like gamma square minus D transpose D, right? Okay, and gamma square minus D. What's D? D is this for I'm really abusing notation. Okay, 0 0 0. Okay, and D 0 0 0. Okay, I guess it's the transpose. Okay, so if we compute this, this is like D transpose D, right? 0 0 0, and this is like, since this is identity, right? Yes, it's okay, let's do it one by one. Okay. Gamma square 0 0 minus dtd 0 0 0, right? And gamma square d transpose d 0 0, and just gamma square. Okay, and we could have written just gamma square d transpose d 0 0, right? Okay, so this is R, and for some reason I'm confusing myself. Okay, okay, here again, and this is the algebraic Riccati equation associated with G dynamic system, right? H Hamiltonian matrix. Okay, and in D1 and U LMIs in control systems, right? After some, yeah, through some, and this is like, yeah, important or sneaky language, I will say. Whenever you see after some manipulations, or it is easy to see that kind of thing, you should get scared a little. Okay, because it might take a one page of manipulations and they will still say it's easy, like there's something, they are sometimes joking as well. Okay, so this is it, and what I'm saying is this: after some manipulation, we have just, I'm just going to write x instead of p here. Okay, by the way, this equation and this equation is literally the same, so don't, I am directly using the book. Okay, Duan and U LMIs in control systems. Okay, and okay, x, no, not x, A transpose x plus C transpose C plus B transpose P plus D transpose C transpose R inverse B transpose P plus D transpose C 0. Okay, again, this is associated with G. Okay, and what we were trying to do, we were trying to obtain the algebraic Riccati equation associated with G hat, right? And if we, okay, I'm gonna use red color now. Here we are going to, whenever we see A, we are going to write A, substitute with A. Okay, and whenever we see B, we are going to substitute it with B epsilon identity. Okay. Whenever we see C, whenever we see C matrix, we are going to substitute it with C epsilon identity. Okay. And last one, whenever we see D matrix, we are going to substitute it with D 0 0 0 matrix. Okay. All right. If we do that, right? Let me get my notes. If we do that, again as written here, there exists a P1 matrix, or X. We were using X, right? There exists a X1 matrix, A plus A transpose X, X1 plus, or should use P like they did in the book. Okay, A transpose P1, I'm just writing like this, plus C transpose C plus B transpose P1 plus D transpose C transpose R inverse B transpose P1 plus D transpose C, and plus epsilon gamma square P1 square plus epsilon square identity. And you're like, where did it came from? It came from, well, it came from first this, right? Because C transpose, right? C transpose and C, it is C transpose C plus epsilon square identity, right? So this term came from this, and again for here we could just write, anyway, like Luan said, after some algebraic manipulation, okay, and again this is 0 equals 0, okay, and since this term, okay, let me zoom in P1 square plus epsilon square identity, okay. All right, this is positive, okay, and this is also positive, okay, by definition epsilon positive, gamma square positive, and P1 is positive, and so does P1 times P1, and okay, this is a positive term, right? And something plus positive term equals 0 indicates that something is less than 0, okay. This is the very advanced explanation here, and so P1 times A transpose P1 plus C transpose C plus B transpose P1 plus D transpose C transpose R inverse B transpose P1 plus D transpose C is less than 0, okay. Alright, so this is it, this is done. We just prove the sufficiency. there exists P or P1 here in this case, such that this given algebraic Riccati equation is less than 0, and I'd like to write this again, copy, paste, right? Can we make it smaller? I guess not. Okay, that's okay. That's okay. This is what it is being implied, right? Alright, we just proved the necessity part, and let's focus on this term again. This is like 1 minute left, I guess. Well, let me use blue color, right? Here, P1 A transpose P1 plus C transpose C, okay, and this term which is B transpose P1 plus D transpose C, right? And the transpose of this term, okay. I want to write this actually, P transpose P1 plus D transpose C transpose, okay. This is symmetric matrix, right? D transpose D minus gamma square, identity, okay, and less than 0 by sure lemma, right? Okay, again this is like R equals square minus identity D transpose D. Let me check if that's correct once again. I just don't want, yeah, okay, because I really don't want to make a mistake at this point. Alright, that's it. So if we have a G, okay, by the way, it's all done, it's QED time now. The proof is done, and now I want to talk about how would we compute. Okay, I want to write this, how to compute H infinity norm, okay, for a given G, okay. Alright, now we have a G of S, right? And we, okay, again, if G of infinite norm of G of S is less than gamma, there exists P positive, right? Such that Okay, and let me write P1, right? P1. This is then LMI, and if we have a gamma, okay, if we have a gamma, we will be able to find a feasible P1 if gamma star is greater than the real gamma, okay, real. If gamma star, that is our estimate, okay, is greater than, this is real gamma, okay, and this is gamma star, this is what we use, okay. So let's say gamma real is 11.4, and if we use, for example, 11.7, okay, in that case, for that gamma star, we will be able to find a feasible P1 star, okay. All right, so the bisection algorithm now is this. Here, this is gamma min, and this is gamma max. Actually, okay, here again, and we are going to first determine gamma min and gamma max, and let's say we are expecting for the H infinite norm of our G dynamical system to be at most 100, okay, and we can say gamma max is 1000, okay. This is like really, we just want to make sure that this is really greater than the real gamma, okay, the real norm. Alright, and this can be really small numbers like 0.000 or something, right? And then we are going to find gamma test gamma test, okay. It looks like gamma transpose, so gamma test, okay, and gamma test is gamma max, right, plus gamma min, okay, average of them, okay. All right, so all right, and we are going to solve this LMI feasibility problem. What is this? What is that feasibility problem? It is this, okay. I shouldn't repeat like so many times here, okay. Right, and by the way, I'm going to show how to do that on using YALMIP, okay, YALMIP, right, in MATLAB, okay, and feasible problem. If we are able to find a P, okay, that means gamma gamma t is really an upper bound. Okay, it's really an upper bound. Okay, so we are going to use now gamma max 2, gamma max 2. We are just going to, okay, this is I'm not explaining it very good. We are going to change gamma max by gamma test. If LMI is feasible. Okay, we're going to do like that. However, if the LMI is not feasible, what I'm trying to say is this: if H infinite norm of G, we have a gamma t, right? We have a gamma t is not an upper bound of the H infinite norm of G, right? Then LMI is not feasible. The YALMIP or another solver, LMI solver that you're using, will state infeasible. Okay, warning on the screen. Okay, and okay, if that is not feasible, that means that gamma t will be a lower bound of our gamma real estimate. Okay, if LMI is infeasible. Okay, and after that again we are going to compute gamma t by using gamma max plus gamma min by averaging them. Okay, and then again we are going to do this step. Okay, update step, and after a while we are going to reach gamma max minus gamma min divided by gamma max. We are going to reach, this is less than our epsilon. Okay, maybe 0.001 or something. Okay, alright, and let me get my book because I really want to write this, the algorithm, bisection algorithm. This is bisection algorithm in a range, okay, formally fashion. Bisection algorithm. Alright, A bisection algorithm. Okay, A, select gamma max upper bound and gamma min lower bound such that gamma min and gamma max is like this. B, if gamma max minus gamma min divided by gamma min, I'm writing directly from the Zeus Essential of Robust Control book. Okay, less than or equal to specified levels. This is like epsilon, okay, like 0.0001 or something, okay. If that's correct, stop, hammer time, okay. And otherwise as go to the next step, which is set gamma t equals gamma max plus gamma min average, okay. Test if by solving or by checking the feasibility, okay. If it's feasible, that means, okay, test if feasible, that means that's correct, okay. And gamma t is an upper bound, so change gamma max with this gamma t, okay, and keep gamma min as is, okay. If feasible, do this as mean feasible, that means gamma t is a lower bound, okay. Gamma t is not greater than h infinite norm, so gamma t is a lower bound, so change gamma min by this gamma t, okay. Update the terms, gamma min and gamma max. Alright, considering this if condition, and go back to step B, okay. I would say, okay, go back to step B. Okay, I want to write go back to step B, or rather we could also write wire, right? This is like a wire statement, so I really want to write this one more time. Copy, paste, okay. This is actually not if, this is actually while this is not correct. While this is not correct, Okay, here this is the condition, and this is like this is end, and we don't need to say go back to step B, right? And here we can write display gamma max and gamma min at each step. Okay, so we can here this is gamma max in the first iteration, here this is gamma min in the first iteration, and this is, let's say this is the correct value. Okay, it is going to be like this, and after a while dot we get this. Okay, and this will be gamma rear. This is like gamma rear head. This will be really close to gamma rear. Okay, depending on our precision, depending on our specified precision level. And yeah, this is it. So I'm trying to, okay, I will also try to show this YALMIP implementation. There is a really good example in Kemin Zhu's book. Okay, Kemin Zhu's book. Okay, I'm going to show that, and this is bisection algorithm. Okay,